What if I told you that everything we can see, the stars, the galaxies, even our own planet, makes up less than 20% of the universe's total mass? The rest is a ghostly presence, an invisible force that defies detection yet holds the cosmos together. This is the mystery of dark matter, a cosmic phantom that has eluded scientists for decades. But it's not alone. There's another enigma lurking in the void: cosmic energy, a mysterious force accelerating the expansion of the universe. Together, these phenomena challenge the very foundations of physics, forcing us to rethink what we know about reality itself. Picture this: you're standing in a pitch-black room, surrounded by objects you can't see but know are there because you feel their weight, their pull. That's how scientists study dark matter. By observing its gravitational effects on the visible universe, galaxies spin faster than they should, light bends in ways it shouldn't, and entire clusters move as if tugged by unseen hands. Meanwhile, cosmic energy acts like an anti-gravity force, pushing the universe apart at an ever-increasing speed. It's as if the cosmos is playing a game of tug-of-war with itself, and we're only just beginning to understand the rules. This isn't just a story for astronomers or physicists, it's a puzzle that affects all of us. Dark matter and cosmic energy shape the fate of the universe, from the birth of galaxies to the ultimate destiny of everything. What we discover about them could redefine our place in the cosmos, answering questions we've asked for millennia. What is the universe made of? How did it begin? And where is it all heading? Over the next few minutes, we'll explore the boldest theories, the most daring experiments, and the brilliant minds racing to solve these mysteries. By the end, you'll see the night sky not just as a collection of stars, but as a canvas hiding secrets we're only beginning to uncover. To understand dark matter, we have to think beyond what our eyes can perceive. Imagine trying to study the wind. You can't see it, but you feel its push, watch it bend trees, and see it carry leaves. Dark matter works the same way. It doesn't glow, reflect, or block light, yet its gravity shapes the universe in ways we can measure. Take galaxies, for example. They spin so fast that, by all known laws of physics, they should tear themselves apart. But they don't, because an unseen mass, dark matter, acts like cosmic glue, holding them together with its gravitational pull. The hunt for dark matter's identity has led scientists to some fascinating possibilities. One leading candidate is weakly interacting massive particles, or WIMP. These hypothetical particles barely interact with normal matter, passing through Earth and even us like ghosts. Then there are axions, another theoretical particle so lightweight and elusive they'd slip through detectors unnoticed. But here's the catch: despite decades of searching, neither WIMP nor axions have been directly observed. Underground labs, particle colliders, and even experiments in space have come up empty so far. This only deepens the mystery. Could dark matter be something even stranger, something we haven't imagined yet? What makes dark matter so critical is that without it, the universe would look entirely different. Early in cosmic history, its gravitational pull gathered clouds of gas into the first galaxies. Today, it weaves an invisible web stretching across the cosmos, guiding the motion of stars and entire galaxy clusters. If you removed dark matter, the night sky would be nearly empty. No spiral galaxies, no majestic clusters, just scattered stars drifting apart. That's how fundamental it is. Yet for all its influence, dark matter remains frustratingly out of reach. Every experiment that fails to detect it forces us to rethink our assumptions, pushing the boundaries of physics further. This isn't just a gap in our knowledge, it's a doorway to discoveries that could rewrite the rules of reality. While dark matter acts as the universe's invisible scaffolding, cosmic energy is the enigmatic force working in the opposite direction, pushing the cosmos apart with relentless power. Imagine blowing up a balloon with dots on its surface. As you inflate it, the dots move away from each other. Now picture that balloon expanding faster and faster over time, as if some unseen hand keeps adding more air. That's what cosmic energy is doing to our universe. Unlike gravity, which draws matter together, this mysterious force accelerates the expansion of space itself, stretching galaxies away from one another at speeds that defy expectations. The discovery of cosmic energy came as a shock to astronomers in the late 1990s. By studying distant supernova exploding stars whose brightness reveals their distance, scientists expected to find the universe's expansion slowing down due to gravity. Instead, they found the opposite. The universe wasn't just expanding, it was speeding up, as if some hidden energy were overpowering gravity's pull. This revelation turned cosmology on its head, earning the researchers a Nobel Prize and forcing physicists to confront a startling truth. Nearly 70% of the universe's energy is something we don't understand. So what could cosmic energy actually be? One leading idea traces back to Einstein himself. He proposed a cosmological constant, a built-in energy of empty space that could balance the equations of general relativity. At the time, he dismissed it as his greatest blunder, but today it might be the closest clue we have. If space itself contains an innate energy, constantly generating more as the universe expands, that could explain the accelerating expansion. But there's a problem. When physicists calculate how strong this energy should be based on quantum theory, the numbers are off by a factor of 1 followed by 120 zeros. That's not just a small error, it's the largest mismatch in science. Alternative theories suggest cosmic energy isn't constant at all. Some propose it's a dynamic field, like an invisible fluid filling space, whose strength changes over time. Others speculate it could be a sign of extra dimensions or even a flaw in Einstein's theory of gravity. The truth is, every explanation so far comes with its own puzzles. What's undeniable is that cosmic energy holds the keys to the universe's fate. If it continues to dominate, galaxies will eventually vanish over the horizon of space, leaving future civilizations with an empty, dark sky. But if this energy evolves or fades, the cosmos could face a very different destiny, one we're only beginning to glimpse. The story of dark matter and cosmic energy isn't just about modern telescopes or supercomputers. It's a tale of human curiosity stretching back nearly a century. It all started in 1933 when a sharp-eyed astronomer named Fritz Zwicky noticed something bizarre about the Coma cluster, a group of galaxies millions of light years away. The galaxies were moving so fast that, according to the laws of gravity, they should have flown apart long ago, but they didn't. Zwicky proposed an audacious idea. There must be invisible matter holding them together, something he called Dunkel Materie, a dark matter. At the time, most scientists dismissed it as a fringe theory. After all, how could the universe be filled with something no one could see? Decades later, another astronomer, Vera Rubin, stumbled upon the same mystery while studying the rotation of galaxies. She expected stars at the edges of spiral galaxies to move slower than those near the center, just like planets farther from the Sun orbit more slowly. But her observations revealed the opposite. Stars at the outskirts were whipping around just as fast as those near the core. The only explanation, an enormous halo of unseen matter, its gravity gripping the stars like an invisible hand. Rubin's work turned Zwicky's speculation into undeniable fact, proving that dark matter wasn't just a curiosity, it was the universe's hidden architecture. The discovery of cosmic energy followed a similar path of unexpected twists. For most of the 20th century, astronomers assumed the universe's expansion was slowing down, thanks to gravity's relentless pull. Then, in 1998, two independent teams studying distant supernova made a jaw-dropping realization. These exploding stars weren't just receding, they were accelerating away from us, as if some repulsive force were overpowering gravity. The implications were staggering. Not only was most of the universe's matter invisible, but an even larger portion of its energy was completely unknown, driving the cosmos apart at an ever-increasing pace. These breakthroughs didn't just add new pieces to the puzzle, they shattered the entire picture. Suddenly, the stuff we could see, stars, planets, gas, accounted for less than 5% of the universe's total content. The rest was a cosmic riddle: 25% dark matter, 70% cosmic energy. It was as if we'd spent centuries studying the ocean by only looking at the foam on its surface, oblivious to the depths below. Each discovery forced scientists to confront how little we truly understood, humbling even the most brilliant minds. Yet these mysteries also ignited a new era of exploration, proving that the universe still holds secrets waiting to be uncovered by those daring enough to look beyond the visible. Gravity is the silent fingerprint of dark matter, the only way we can sense something that refuses to be seen. Think of it like a game of cosmic hide and seek, where dark matter never steps into the light but leaves its mark everywhere through the force of gravity. One of the most stunning examples of this is gravitational lensing, a phenomenon where dark matter's immense gravitational pull warps the fabric of space itself, bending light from distant galaxies like a lens. When astronomers look at clusters of galaxies, they sometimes see stretched or distorted images of objects behind them, a telltale sign of dark matter's invisible hand reshaping the path of light. It's as if the universe is showing us shadows of something far greater than what meets the eye. These observations reveal something extraordinary. Dark matter isn't just scattered randomly, it forms vast, intricate structures. Supercomputer simulations show it weaving colossal halos around galaxies, like invisible cocoons holding them together. Without these halos, galaxies would fly apart. Stars on the outer edges rotate at speeds that defy the laws of gravity as we know them, yet they stay bound in place, tethered by the gravitational grip of something unseen. It's like watching a carousel spin at full speed with no one holding on, yet no one flies off. The only explanation, an unseen force far stronger than anything visible, is keeping everything in balance. But here's the puzzle. If dark matter is everywhere, shaping the universe on the grandest scales, why can't we pin down what it's made of? Gravity tells us where it is, but not what it is. We know it doesn't interact with light or ordinary matter aside from its gravitational pull. It doesn't collide with atoms, emit radiation, or leave behind any trace except its weight in the cosmos. Some theories suggest dark matter particles could be passing through us right now, millions every second without a single interaction. It's like standing in a crowd of ghosts. You feel their presence, but no matter how hard you reach out, your hand passes right through. This gravitational dance isn't just about holding galaxies together. It's about building them in the first place. In the early universe, dark matter acted as a cosmic scaffold, its gravity pulling clouds of gas into the dense knots that eventually ignited into stars. Without it, the universe would be a vast, empty sea of scattered gas, devoid of the galaxies and structures we see today. Yet for all its importance, dark matter remains the ultimate cosmic tease. We see its effects everywhere, but the closer we get to understanding its true nature, the more it slips away. Every experiment that fails to detect it only deepens the mystery, leaving us with a profound question. Are we missing a fundamental piece of physics, or is the universe playing by rules we haven't even imagined yet? Dark matter and cosmic energy might both be invisible, but they're locked in a cosmic tug of war with opposite agendas. Picture two titans wrestling over the fate of the universe, one pulling everything together, the other pushing it apart. Dark matter is the architect, sculpting galaxies and clusters with its gravitational grip. Without it, stars would scatter like marbles on a tilted table, never forming the majestic spirals and colossal clusters we see today. Cosmic energy, on the other hand, is the force tearing the cosmic fabric at its seams, accelerating the expansion of space itself. It's as if the universe is stretching faster than its own blueprint intended, and no one knows why. What's truly mind-bending is the scale of their dominance. Combined, dark matter and cosmic energy make up 95% of the universe's total content. That leaves just 5% for everything we can actually see: planets, stars, nebulae, even ourselves. Think about that for a moment. All the galaxies, all the light, all the beauty we observe through telescopes is just the faintest glimmer in a sea of darkness. It's like studying a painting by only examining the frame, oblivious to the vast canvas hidden in shadow. This imbalance isn't just a curiosity, it's a crisis for modern physics. Our best theories, from Einstein's relativity to quantum mechanics, were built to explain the behavior of ordinary matter. They crumble when faced with the reality that most of the universe operates by rules we don't yet understand. Take gravity, for example. It works perfectly to describe how planets orbit stars or apples fall from trees. But when applied to galaxy clusters or the universe's expansion, the math falls apart unless we invoke these invisible giants. It's like trying to solve a puzzle with 95% of the pieces missing. The tension between dark matter and cosmic energy isn't just theoretical, it's shaping the universe's destiny. Dark matter's gravity tries to slow the expansion, pulling galaxies closer like a cosmic glue. Cosmic energy fights back, stretching space faster and faster, as if the universe is determined to outrun its own shadow. Right now, cosmic energy is winning. Billions of years from now, if this continues, galaxies beyond our own will vanish over the horizon, their light never reaching us again. The universe will grow cold, dark, and eerily empty. But if dark matter gains the upper hand, the expansion could slow, even reverse, collapsing everything back into a single point. The stakes couldn't be higher. Scientists are racing to untangle this mystery, because understanding these forces isn't just about mapping the cosmos, it's about rewriting the laws of physics. Some theories suggest dark matter and cosmic energy might be two sides of the same coin, aspects of a deeper, unified force we haven't discovered yet. Others propose they're entirely separate, one a particle, the other a property of space itself. Every experiment, from underground detectors hunting dark matter to telescopes measuring the universe's expansion, brings us closer to answers or deeper into the maze. One thing's certain, the universe is far stranger, far richer than we ever imagined. And the greatest discoveries lie not in the stars we see, but in the darkness between them. The Lambda-CDM model is the closest thing we have to a cosmic instruction manual, a framework that stitches together everything we know about dark matter and cosmic energy into a single, elegant theory. At its heart are two key ingredients: lambda, representing the mysterious cosmic energy driving the universe's accelerated expansion, and cold dark matter, the invisible glue holding galaxies together. This model doesn't just explain the universe we see today, it traces its entire history, from the first flickers of light after the Big Bang to the sprawling web of galaxies we observe now. One of its greatest triumphs is how it decodes the cosmic microwave background, the afterglow of the Big Bang. Imagine tuning an old television to static. those snow-like flickers are faint echoes of the universe's birth. The Lambda-CDM model predicts the precise patterns in that static, matching observations with stunning accuracy. It also explains why galaxies cluster like glitter spilled on a table, forming filaments and voids that stretch across billions of light years. Without cold, dark matter's gravitational pull, those structures would never have formed, and without cosmic energy's push, the universe wouldn't be accelerating apart as it does. But even the best models have cracks. Take the Hubble tension, a stubborn discrepancy in measurements of how fast the universe is expanding. Some methods, like tracking distant supernova, give one number. Others, like studying the cosmic microwave background, give a slightly different one. It's as if two clocks, both perfectly calibrated, started ticking at different speeds. This isn't just a small error, it's a gap that could hint at entirely new physics. Maybe cosmic energy isn't constant after all. Maybe dark matter interacts in ways we haven't accounted for. Or perhaps gravity itself behaves differently on cosmic scales. The Lambda-CDM model's success is a double-edged sword. It fits so much data so well that any challenge to it feels like shaking the foundations of cosmology itself. Yet science thrives on such shake-ups. For decades, Newton's laws seemed perfect until Einstein showed they were just a special case of a deeper truth. The Lambda-CDM model could be facing a similar moment. Some theorists are exploring tweaks like dark energy that evolves over time or dark matter with a faint ability to interact with light. Others are venturing further, proposing radical ideas like modified gravity or extra dimensions. What's at stake isn't just a set of equations, it's our understanding of reality. The Lambda-CDM model is more than a theory. It's a lens through which we interpret the universe's past, present, and future. If it's correct, the cosmos will keep expanding until galaxies fade into darkness. If it's wrong, the universe's fate might be far stranger than we've dared to imagine. Every new telescope, every deeper simulation, every unexplored particle hypothesis brings us closer to the truth. And in that pursuit, even the most elegant models must bow to the ultimate authority, the universe itself. WIMP represent one of the most compelling solutions to the dark matter puzzle, particles that could be hiding in plain sight, passing through our world unnoticed every second. Imagine standing in a snowstorm where every snowflake is a WIMP. Trillions would drift through your body every moment without a single collision, their only trace being the faintest gravitational whisper. These weakly interacting massive particles are thought to be heavy, perhaps 10 to 100 times the mass of a proton, yet they shun ordinary matter so completely that detecting them feels like trying to catch smoke with bare hands. The hunt for WIMP has driven some of the most ambitious experiments in science. Deep underground, shielded from cosmic rays by layers of rock, detectors filled with ultra-pure liquids or crystals wait for the once-in-a-lifetime moment a WIMP might bump into an atomic nucleus. Facilities like the Large Underground Xenon Experiment, or LUX, operate in near-total silence, their sensors tuned to catch the tiniest ripple of energy, a potential fingerprint of dark matter. Meanwhile, particle colliders like the Large Hadron Collider smash protons together at nearly the speed of light, hoping to briefly conjure WIMP from the energy of the collisions. It's a cosmic game of hide and seek where the hider doesn't just avoid being seen, it barely acknowledges the game exists. What makes WIMP so tantalizing is how neatly they fit into existing physics. They emerge naturally from theories like supersymmetry, which proposes every known particle has a heavier, invisible twin. If WIMP exist, they'd have flooded the universe moments after the Big Bang, their sheer abundance explaining the gravitational scaffolding we observe today. They're the Goldilocks candidate, not too light, not too heavy, not too interactive, just right to match the cosmos' hidden architecture. Yet after decades of searching, not a single confirmed WIMP signal has appeared. Detectors grow more sensitive, colliders reach higher energies, and still the results come back empty. This absence isn't just frustrating, it's provocative. Each failed experiment forces physicists to rethink WIMP's possible traits, adjusting theories to accommodate the silence. Maybe WIMP are lighter than we thought, or interact even more weakly than predicted. Maybe they're not particles at all, but something stranger, like primordial black holes or fragments of higher dimensional space. The longer WIMP evade detection, the more we're reminded how little we truly know about the universe's hidden layers. Yet the search continues, because finding them wouldn't just solve the dark matter mystery, it would open a new chapter in physics, revealing a shadow universe that's been with us all along, unseen and untouchable, yet holding everything together. While WIMP have dominated the dark matter conversation for decades, there's another contender in the shadows, one so lightweight it could rewrite the rules of particle physics. Meet the axion, a hypothetical particle so small it makes an electron look like a boulder in comparison. Born not from dark matter theories, but from an entirely different puzzle in quantum physics, axions emerged as a solution to the strong CP problem, a quirk in the equations governing the forces inside atomic nuclei. The math demanded a particle with bizarre properties, vanishingly tiny mass, no electric charge, and an almost ghostly reluctance to interact with ordinary matter. And as it turns out, those same traits make axions a perfect fit for dark matter. Picture the universe filled not with heavy, sluggish WIMP, but with an ocean of ultra-light axions, billions of times lighter than electrons, flowing through space like an invisible tide. Unlike discrete particles, axions would behave more like waves, their collective mass weaving through galaxies in ripples so subtle we'd never notice except for their gravity. This wave-like nature could explain why dark matter seems so smoothly distributed, avoiding the clumpy structures heavier particles would create. It's a radically different vision of the cosmos, where the missing mass isn't made of scattered boulders but of mist, a fine, uniform haze sculpting the universe from within. The hunt for axions is just as unconventional as the particles themselves. While WIMP detectors rely on catching rare collisions, axion experiments play a more delicate game. Take the axion dark matter experiment, or ADMX. It uses a powerful magnetic field to coax axions into revealing themselves. Here's how it works. If axions exist, the magnetic field should nudge them to convert into photons, particles of light, which a super-sensitive radio receiver can then detect. It's like tuning an old-fashioned radio dial, searching for a station broadcasting on a frequency no one's ever heard before. The challenge: the signal would be unimaginably faint, a whisper drowned out by the universe's background noise. What makes axions so tantalizing is their dual promise. Solving dark matter would be groundbreaking enough, but axions could also crack one of particle physics' most stubborn puzzles, the strong CP problem. In simple terms, the equations describing the nuclear force inside atoms suggest there should be way more asymmetry between matter and antimatter than we observe. Axions elegantly balance these scales, acting as a cosmic reset button that keeps the universe's symmetry in check. It's rare for a single theoretical particle to answer two colossal questions at once, like finding a key that unlocks two different treasure chests. Yet for all their potential, axions remain elusive. Experiments like ADMX have ruled out certain mass ranges, narrowing the search, but the needle in a haystack challenge persists. Unlike WIMP, axions are so light that their signals could be drowned out by the faintest interference, thermal noise, cosmic rays, even vibrations from passing trucks. Some theorists have even proposed that axions might interact so weakly that current technology could never detect them, pushing the boundaries of what's measurable. But that hasn't stopped the search. New approaches are emerging, from quantum-enhanced sensors to repurposed MRI machines, all chasing the same goal: to catch the faintest ripple in the cosmic mist. The axion story reminds us how interconnected physics truly is. A particle dreamed up to fix a quantum quirk might hold the key to the universe's missing mass. And if axions are real, they'd reveal a cosmos far stranger than we imagine, and one where the heaviest structures are built from the lightest things, where waves in an invisible C-shaped galaxies, and where answers to today's greatest mysteries might be hiding in the quietest corners of quantum theory. Whether they are out there or not, axions prove one thing: the universe's secrets rarely lie where we first think to look. What if the problem isn't missing matter, but misunderstood gravity? That's the bold question at the heart of modified gravity theories, a radical rethinking of how the universe holds itself together. Instead of invoking invisible dark matter, these ideas suggest we've been looking at the cosmic puzzle backward. Maybe galaxies behave strangely not because of some unseen mass, but because gravity itself works differently on vast scales than our equations predict. It's like realizing the rules of chess you've always used don't apply in deep space. The pieces move in ways that demand a whole new rulebook. Leading this charge is modified Newtonian dynamics, or MUND, a theory that tweaks gravity's behavior where its pull grows exceptionally weak. Picture a playground merry-go-round. Push it gently and it barely spins. Push harder and it accelerates predictably. But MUND suggests that below a certain threshold, a whisper of acceleration 10 billion times weaker than Earth's gravity, the rules change. At these scales, gravity might strengthen slightly, mimicking the extra pull we've attributed to dark matter. Remarkably, MUND accurately predicts the rotation speeds of many galaxies without invoking a single invisible particle. It's as if the cosmos has been whispering a hint. The answer might not lie in what's missing, but in how we've misread the forces at play. Yet MUND faces its own cosmic hurdles. While it excels at explaining individual galaxies, it stumbles when confronted with the titanic collisions of galaxy clusters. Observations of the Bullet cluster, for instance, two clusters smashing through each other at millions of miles per hour, show gravitational effects that appear displaced from the visible matter, as if something massive but unseen is leading the charge. MUND struggles to explain this without reintroducing some form of hidden mass. Then there's the cosmic microwave background, the Big Bang's afterglow, whose intricate patterns align neatly with dark matter models but resist MUND adjustments. It's like solving half a crossword puzzle perfectly only to realize the remaining clues demand a different set of answers. These challenges haven't deterred theorists from exploring even bolder ideas. Some propose gravity leaks into extra dimensions at cosmic scales, weakening its apparent strength where we'd expect dark matter's grip. Others suggest space-time itself has a kind of elasticity, stretching differently around galaxies than around stars. These theories venture beyond mere tweaks to Newton or Einstein. They reimagine gravity as something dynamic, context-dependent, even evolving over time. Imagine if gravity were more like weather, predictable in familiar conditions, but full of surprises when you step into the universe's extreme environments. What makes modified gravity so compelling is its sheer audacity. It forces us to confront an uncomfortable truth. After centuries of scientific progress, we might still not fully grasp one of nature's most fundamental forces. Every unexplained galactic rotation or cluster collision could be a clue, not to dark matter's existence, but to gravity's hidden complexities. Yet the debate is far from settled. For every success man achieves, traditional dark matter models counter with their own triumphs, like simulating the universe's large-scale structure with uncanny precision. This isn't just a scientific disagreement, it's a clash of philosophies. Do we fill the gaps with unseen substances or rewrite the laws we thought were settled? Perhaps the most exciting outcome isn't which theory wins, but what we learn in the struggle. Modified gravity pushes cosmology to its limits, testing the resilience of general relativity in ways Einstein never could have imagined. Even if dark matter ultimately prevails, the questions raised by Mond have already deepened our understanding of gravity's nuances. After all, science thrives not on certainties, but on the tension between what we know and what we've yet to discover. And in that space of uncertainty, between the pull of tradition and the push of innovation, lies the next great breakthrough, whether it's a new particle, a new law, or something no one has dared to dream yet. Imagine the emptiest place you can think of, a void where not a single atom lingers. Now picture that same space crackling with invisible energy, particles flickering in and out of existence so fast they evade detection. This isn't science fiction, it's the quantum vacuum, a seething sea of potential that defies our classical notions of nothingness. According to quantum mechanics, empty space is anything but empty. Virtual particles, ghostly pairs of matter and antimatter, constantly pop into existence, borrowing energy from the vacuum before vanishing again in fractions of a second. These fleeting disturbances aren't just theoretical quirks. They might hold the key to one of cosmology's greatest mysteries, the nature of dark energy. The connection lies in a startling idea. What if the energy of this quantum vacuum isn't just background noise, but the very force accelerating the universe's expansion? Einstein's cosmological constant, a mathematical placeholder he once discarded, could find its physical reality in these quantum fluctuations. The math seems tantalizingly simple. Add up all the energy from these virtual particles, and you'd expect it to manifest as a repulsive force, stretching space-time apart. But here's where the puzzle deepens. When physicists actually perform those calculations, the numbers are catastrophically off. The predicted vacuum energy is a staggering one, followed by 120 zeros times stronger than the dark energy we observe. It's like expecting a hurricane and feeling only a breeze, a discrepancy so vast it's been called the worst theoretical mismatch in all of physics. This isn't just a minor hiccup, it's a crisis at the heart of modern physics. The cosmological constant problem exposes a glaring rift between quantum mechanics and general relativity, two pillars of science that refuse to align. Quantum theory treats particles and fields as discrete, probabilistic entities, while Einstein's gravity describes spacetime as a smooth, continuous fabric. When forced to coexist in calculations, they produce nonsensical results, like trying to mix oil and water. Some theorists argue the solution lies in subtracting away infinite quantities through mathematical tricks, but these feel like band-aids on a gaping wound. Others propose more radical fixes. Maybe virtual particles gravitate differently than real ones, or perhaps the vacuum's energy is mysteriously screened on cosmic scales, leaving only a faint residue we call dark energy. The stakes couldn't be higher. If the quantum vacuum is indeed the source of dark energy, we're staring at a cosmic irony. The same phenomenon that fuels the universe's expansion also threatens to unravel our understanding of reality. Resolving this could demand a revolution as profound as relativity or quantum theory themselves, a framework where gravity and the quantum world finally reconcile. Candidates like string theory or loop quantum gravity offer glimpses of such a unification, but so far, none have delivered a definitive answer. What's clear is that the vacuum isn't the static void we once imagined. It's a dynamic, enigmatic medium, whispering clues about forces that shape the cosmos. And until we decode its language, the true nature of dark energy will remain one of science's most tantalizing enigmas. String theory paints a picture of reality far stranger than our everyday experience, one where the universe hums with hidden dimensions, and particles are replaced by dancing threads of energy. Imagine plucking a guitar string. The pitch changes depending on how tightly it's stretched and how vigorously it vibrates. Now shrink that string down to a billionth of the size of an atom, and you've got the basic idea. In this framework, every particle we know, electrons, quarks, photons, is just a different vibrational note played by these microscopic strings. But here's the twist. These strings don't vibrate in the 3 dimensions we're familiar with. They require at least 10 dimensions to make the math work, meaning our universe could be floating in a higher dimensional space like a sheet of paper suspended in a vast, unseen library. This raises a fascinating possibility. What if dark matter isn't some exotic particle but ordinary matter we simply can't perceive because it's trapped in a parallel dimension? In certain versions of string theory, our universe might be a 3-dimensional brane, short for membrane, drifting alongside others in a higher dimensional bulk. Matter on a nearby brane could exert gravitational influence on ours, tugging at galaxies and bending light in ways we attribute to dark matter. It's like hearing footsteps in an empty hallway. You know something's there, but you can't see the source. These hidden dimensions could also explain dark energy. If branes occasionally collide or ripple, the energy from these interactions might seep into our universe as a repulsive force, accelerating cosmic expansion. The elegance of string theory is undeniable. It elegantly unites quantum mechanics and gravity, 2 realms of physics that have resisted reconciliation for a century. It transforms the chaotic zoo of subatomic particles into harmonious vibrations of a single underlying substance. Yet for all its mathematical beauty, string theory faces a glaring challenge. We have no experimental proof it's correct. The strings themselves are too tiny to observe with current technology, and the extra dimensions, if they exist, are curled up into shapes so small they evade detection. Some critics argue that without testable predictions, string theory veers closer to philosophy than science. Others counter that its very difficulty hints at a deeper truth, that reality's ultimate nature might be stranger than our tools can currently grasp. This tension between elegance and evidence makes string theory one of the most polarizing ideas in physics. Some researchers devote careers to exploring its intricate equations, convinced they hold the key to the universe's deepest secrets. Others dismiss it as a dead end, a beautiful mirage with no connection to observable reality. But perhaps the truth lies in between. Even if string theory never produces a smoking gun discovery, its mathematical tools have already enriched other areas of physics, from black hole thermodynamics to quantum computing. Like a compass pointing toward uncharted territory, it keeps pushing scientists to ask questions they might never have considered otherwise. What's undeniable is that string theory forces us to confront how limited our perception might be. We're 3-dimensional creatures trying to decode a universe that could be built on entirely different blueprints. Dark matter and dark energy, those twin enigmas, might not be missing pieces of our puzzle. They could be clues that we've been holding the puzzle upside down all along. Whether string theory ultimately proves right or wrong, it reminds us that the cosmos has a habit of outrunning our imagination, leaving us to chase shadows in dimensions we can't yet see. What if our universe isn't unique, just one page in an infinite cosmic library, each volume with its own set of physical rules? This is the Multiverse Hypothesis, a daring idea that might explain dark energy's mysteriously fine-tuned value. Think of it like a cosmic lottery. Out of countless universes bubbling into existence, each with random constants, ours won the jackpot. A dark energy density just right for galaxies to form, stars to ignite, and life to emerge. Too much dark energy and space would have expanded too quickly for matter to clump together. Too little, and gravity would have crushed everything back into a hot, dense singularity. We find ourselves in a universe where the numbers align perfectly, not by design, but by sheer chance among infinite possibilities. This line of thinking, called anthropic reasoning, doesn't explain why dark energy has its specific value. Instead, it suggests that only in universes where conditions allow observers like us to exist could the question even be asked. It's like a fish wondering why water is perfectly suited to its gills. The answer isn't about water's properties, but about the fact that fish couldn't exist to ponder it otherwise. Some physicists argue this approach is a cop-out, abandoning the search for deeper laws. Others see it as a profound shift. If fundamental constants aren't inevitable but random, science must grapple with a cosmos where our universe is just one outcome in a vast ensemble of realities. The multiverse idea isn't pure speculation. It emerges naturally from theories like eternal inflation, where space-time continually sprouts new universes like bubbles in an infinite champagne glass. Each bubble universe could have different physics, with dark energy's strength determined by the roll of cosmic dice. String theory adds another layer, suggesting there might be 10 to the 500 possible vacuum states, each corresponding to a universe with unique constants. In such a landscape, it's statistically inevitable that at least one universe would land on the numbers we observe. Yet this hypothesis sparks fierce debate. Critics argue it's untestable. If other universes are forever beyond our reach, how can we prove they exist? Supporters counter that indirect evidence might lurk in the cosmic microwave background, where collisions with other universes could leave faint imprints. Others propose that the multiverse isn't just a scientific idea but a philosophical necessity. The only way to make sense of dark energy's improbable value without invoking unexplained fine-tuning. At its core, the multiverse hypothesis forces us to confront what science should explain. Must every answer derive from fundamental laws, or can statistics across infinite realities suffice? It's a question that blurs the line between physics and metaphysics, challenging us to reconsider not just the universe's structure, but the very nature of explanation itself. Whether the multiverse is a groundbreaking insight or a dead end, one thing is certain: it reveals how deeply the mystery of dark energy is entwined with our understanding of reality's deepest fabric. The hunt for dark matter isn't just about theories, it's a high-stakes game of hide and seek played out in laboratories, deep underground caverns, and even outer space. Scientists have deployed 3 major strategies to catch this elusive cosmic fugitive, each with its own strengths and tantalizing near misses. First, there's direct detection, where ultra-sensitive instruments lie in wait for the unimaginably rare moment a dark matter particle might bump into ordinary matter. Picture a vault a mile beneath the Earth's surface, shielded from cosmic rays, housing a tank of liquid xenon chilled to near absolute zero. This is the heart of experiments like LUX Zeppelin and Xeno NNT, where scientists monitor for tiny flashes of light or electrical signals, potential fingerprints of a dark matter collision. It's like listening for a single raindrop in a thunderstorm, requiring detectors so precise they can sense disturbances smaller than an atom's width. Then there's indirect detection, turning the universe itself into a dark matter observatory. Instead of waiting for particles to come to us, telescopes scan the skies for traces of dark matter annihilating or decaying in space. When 2 dark matter particles collide, theory suggests they could transform into gamma rays, neutrinos, or other high-energy signals. Instruments like the Fermi Gamma Ray Space Telescope search for unexplained bursts of radiation from galaxy cores or dwarf galaxies, where dark matter is thought to cluster densely. It's cosmic forensics hunting for the smoke that might reveal dark matter's fire. One tantalizing clue came from the Milky Way center, where an excess of gamma rays defies conventional explanation. Could this be dark matter's long-awaited signature, or just undiscovered pulsars? The debate rages on. The third approach throws brute force at the problem: particle colliders like the Large Hadron Collider. By smashing protons together at nearly light speed, scientists recreate conditions fractions of a second after the Big Bang, hoping to briefly conjure dark matter into existence. The strategy hinges on Einstein's famous equation, energy morphing into mass. If dark matter particles are light enough, the LHC's collisions might produce them, escaping undetected but leaving behind an energy imbalance in the wreckage. Think of it like a car crash where the damage suggests an unseen passenger fled the scene. While no definitive dark matter signal has emerged, these experiments have ruled out entire classes of particles, narrowing the search like a cosmic game of 20 questions. What makes this three-pronged attack so powerful is how the methods complement each other. Direct detection excels at finding slow-moving, heavy particles that might lurk in our galactic neighborhood. Indirect detection probes high-energy interactions that could occur where dark matter clusters most densely. Colliders, meanwhile, test theories about how dark matter might connect to known particles. Together, they form a net cast across scales, from the quantum realm to the cosmic web. Every null result, every exclusion tightens the constraints, forcing theorists to refine their ideas. The stakes couldn't be higher. Discovering dark matter wouldn't just solve a cosmic mystery, it would open a window into physics beyond the standard model, potentially revealing hidden dimensions, new forces, or even parallel universes. And while the search has stretched decades longer than many expected, each failed experiment teaches us something invaluable. The universe guards its secrets fiercely, but not forever. Whether the breakthrough comes from a flash in a xenon tank, a gamma-ray spike from deep space, or an anomaly in collider data, one thing's certain: when dark matter finally shows its face, it will rewrite the story of the cosmos. To uncover the secrets of dark matter and cosmic energy, scientists turn to the oldest light in the universe, the cosmic microwave background, or CMB. This faint glow, lingering from just 380,000 years after the Big Bang, is like a baby picture of the cosmos, preserving the imprint of forces that shaped everything we see today. Imagine it as the universe's first whisper, carrying echoes of a time when matter and energy were so densely packed that light couldn't travel freely. When space finally cooled enough for atoms to form, photons broke free, streaming outward in all directions. That ancient light, stretched by 13.8 billion years of cosmic expansion, now bathes the universe in microwaves, a background static detectable by radio telescopes. What makes the CMB so invaluable are the tiny imperfections in its temperature fluctuations, no larger than 1 part in 100,000. These minuscule variations aren't random. They're the seeds of cosmic structure, the gravitational footprints of dark matter's invisible hand. Dense regions, slightly cooler in the CMB, mark where dark matter's gravity began pulling matter together, eventually forming galaxies and clusters. The patterns are so precise that they act like a cosmic barcode, encoding the universe's ingredients: roughly 5% ordinary matter, 25% dark matter, and 70% dark energy. The Lambda-CDM model predicts these fluctuations with astonishing accuracy, a triumph of modern cosmology. Yet even this pristine snapshot hides puzzles. The Planck satellite, one of the most advanced CMB mappers ever built, confirmed the broad strokes of our cosmic recipe. but also revealed curious anomalies. Certain large-scale patterns in the CMB appear weaker than expected, as if part of the early universe's story is missing. There's also the cold spot, an unusually large, frigid region that defies standard explanations. Could these be statistical flukes or hints of something deeper? New physics, extra dimensions, or even traces of a pre-Big Bang universe? The CMB's perfection is its greatest strength, but its imperfections might hold the keys to revolutions we've yet to imagine. One of the most profound insights from the CMB is how dark matter's gravity sculpted the cosmos. Ordinary matter, buffeted by radiation pressure in the early universe, couldn't clump efficiently on its own. Dark matter, unaffected by light's push, provided the gravitational backbone, creating wells where atoms eventually pooled. Without it, the universe would lack the intricate web of galaxies we see today. The CMB's fluctuations are essentially dark matter's blueprint, a map of where it began weaving the cosmic tapestry. But there's a twist. The precise spacing of these fluctuations suggests dark matter must be cold, slow-moving enough to let structures form hierarchically, from small clumps merging into larger ones. This aligns with theories like WIMP, but challenges alternatives like ultralight actions, which would leave a different imprint. Cosmic energy leaves its own cryptic signature in the CMB. The patterns of fluctuations reveal not just the universe's composition, but its geometry flat, as far as we can measure, meaning parallel lines never meet. This flatness requires a precise balance between matter's gravity and cosmic energy's repulsion, a balance that seems too perfect to be accidental. The CMB also confirms cosmic energy's dominance in the universe's later epochs, as its repulsive force overcame gravity's grip, sending galaxies speeding apart. Yet the CMB can't tell us whether this energy is truly constant, as Einstein's cosmological constant suggests, or if it evolves over time, a question that could determine whether the universe ends in icy solitude or a dramatic collapse. The beauty of the CMB is that it's both an endpoint and a starting line. It marks the moment the universe became transparent, but also the point where our observational reach currently ends. Beyond it lies the Dark Ages, an era before stars or galaxies, veiled by primordial plasma. Future experiments aim to push further, hunting for even fainter signals, like the elusive B-mode polarization patterns that could reveal gravitational waves from cosmic inflation, or distortions in the CMB caused by dark matter's subtle interactions. Each new layer peeled back brings us closer to understanding the invisible forces that govern existence. The CMB isn't just a relic, it's a living puzzle, challenging us to decode the universe's deepest mysteries one microwave photon at a time. Vera Rubin peered through her telescope at the Andromeda galaxy, expecting to see stars obeying the familiar rules of gravity, slower at the edges, like planets trailing off in our solar system. Instead, she found chaos. Stars far from the galactic center were racing just as fast as those near it, as if some unseen hand had spun the galaxy like a solid disk. According to Newton's laws, these outer stars should have been flung into the void, their speeds too great for the visible matter's gravity to hold them. Yet there they were, clinging to the galaxy's outskirts with inexplicable tenacity. Rubin's meticulous observations in the 1970s didn't just challenge textbooks, they shattered them, revealing a universe where the rules we thought we knew only applied to a fraction of what's actually out there. The implications were staggering. If stars' speeds didn't match the gravity of visible matter, something invisible had to be tipping the scales. Rubin's data pointed to a massive halo of dark matter enveloping each galaxy, its gravity gripping stars like an invisible leash. Picture a merry-go-round spinning so fast the children should fly off, except unseen ropes tether them in place. That's what dark matter does for galaxies. Without it, spiral arms would unravel and billions of stars would scatter into the cosmic dark. Rubin's rotation curves became the smoking gun for dark matter, proving that what we see isn't just a tiny fraction of what's there, it's barely the sprinkles on the cosmic cupcake. Decades later, astronomers still rely on rotation curves, but the tools have grown exponentially sharper. Modern telescopes like the Atacama Large Millimeter Array map the faintest whispers of gas and dust in distant galaxies, tracing their motion with precision Rubin could only dream of. The results confirm her discovery across the cosmos. Galaxy after galaxy rotates too fast at the edges, their stars and gas whipping around as if pulled by phantom mass. Even more revealing, the curves aren't random, they follow a pattern. Dark matter isn't lumped haphazardly around galaxies. It forms smooth, predictable halos, denser at the center and fading outward. This consistency is a nightmare for theories trying to explain the anomaly without dark matter. Modified Newtonian dynamics, or MUND, tweaks gravity's math to fit individual galaxies but stumbles when applied to clusters or the universe's large-scale structure. Rotation curves expose these cracks, showing where alternative theories strain to keep up with the data. The latest twist comes from dwarf galaxies, tiny, faint satellites orbiting larger ones like fireflies around a lantern. These cosmic underdogs rotate just as mysteriously as their giant cousins, but with a puzzling quirk. Their dark matter seems clumped more tightly than models predict. Some scientists argue this could hint at dark matter's hidden properties. Perhaps it interacts with itself in ways we haven't accounted for. Others see it as a challenge to our understanding of galaxy formation itself. Either way, rotation curves remain a Rosetta Stone for decoding dark matter's secrets, bridging the gap between theoretical predictions and the real, whirling chaos of the cosmos. What makes Rubin's discovery so enduring isn't just the evidence it provided, it's the questions it keeps unearthing. Every new galaxy mapped, every subtle deviation in rotation, peels back another layer of the mystery. The stars may be the universe's glitter, but it's the darkness between them, silent and unseen, that holds everything together. And as long as galaxies keep spinning faster than they should, we'll know there's far more to the story than meets the eye. Zoom out far enough, and the universe reveals its grandest design. Not scattered stars or isolated galaxies, but an immense, interconnected web stretching billions of light years across. This cosmic architecture, with its gossamer threads of galaxies and vast, empty voids, is dark matter's masterpiece. Like an invisible sculptor, dark matter's gravity spent billions of years pulling matter into this delicate lattice, a structure so colossal it defies human intuition. Imagine pouring syrup onto a griddle and watching it spread into branching, honeycomb patterns, except here, the syrup is galaxies, and the griddle is the fabric of space-time itself. Supercomputer simulations bring this process to life in astonishing detail. Take the Millennium Run, one of the most ambitious virtual universes ever created. By programming the laws of physics into a digital cosmos, starting with a soupy haze of dark matter, and gas scientists watched as gravity worked its magic. Over 13 billion simulated years, dark matter's pull carved out a web nearly identical to the one we observe through telescopes. The resemblance isn't just striking, it's validation. When a digital universe built solely on our understanding of dark matter mirrors reality so precisely, it's like finding a blueprint for the cosmos hidden in the code. Yet the cosmic web isn't just a pretty pattern, it's a forensic tool. By mapping real galaxies in projects like the Sloan Digital Sky Survey, astronomers compare the simulation's predictions to nature's handiwork. Tiny discrepancies become clues, Maybe dark matter isn't entirely cold but slightly warm, with particles moving fast enough to blur the web's sharp edges. Or perhaps it interacts with itself in ways we haven't accounted for, leaving faint fingerprints in the spacing between galaxy clusters. Every filament, every void, holds information about dark matter's hidden properties waiting to be decoded. What's truly humbling is how much of this structure we can't even see. The luminous galaxies tracing the web's strands are just the glitter sprinkled atop the scaffolding. The real weight comes from the dark matter halos enveloping them. Without this invisible framework, the universe would look utterly different. No grand filaments, no sprawling clusters, just a diffuse mist of gas and stars adrift in the void. The cosmic web isn't just evidence of dark matter's existence. It's proof of its dominance, a reminder that the universe's true skeleton is woven from something we've yet to touch, measure, or even fully comprehend. And the story doesn't end there. The web isn't static, it's a living, evolving entity. Galaxies slide along filaments like beads on a string, drawn toward dense nodes where clusters collide in slow motion. Voids grow emptier as gravity drains matter away, their boundaries sharpening over eons. This dynamic dance is driven by dark matter's relentless pull, a force shaping not just the universe's past and present, but its future. The deeper we probe the web's structure, the more we realize dark matter isn't just a hidden component of the cosmos. It's the architect of everything. If dark matter particles truly exist, they might not just drift silently through the cosmos. They could occasionally crash into each other, annihilating in bursts of energy detectable from Earth. Picture two ghostly particles colliding in the void, vanishing in a flash of gamma rays or other high-energy signals. This isn't science fiction. It's a leading strategy in the hunt for dark matter, turning the universe into a vast laboratory where telescopes act as cosmic eavesdroppers. The Fermi Large Area Telescope, or Fermi LAT, has spent over a decade scanning the skies for these elusive whispers, particularly from regions where dark matter is thought to pile up like snowdrifts, galactic centers, dwarf galaxies, and clusters where gravity herds invisible particles into dense crowds. One of the most tantalizing clues emerged from the heart of our own Milky Way. Astronomers poring over Fermi LAT data noticed an odd excess of gamma rays, a diffuse glow of high-energy light with no obvious explanation. Dubbed the Galactic Center GVXS, this signal matches predictions for certain types of dark matter annihilation, as if somewhere in the galaxy's bustling core, unseen particles were colliding and dissolving into light. The excitement was palpable here. At last might be dark matter's fingerprint, but the cosmos is rarely so straightforward. Other explanations crept in. Perhaps the gamma rays came from undiscovered pulsars, the spinning corpses of dead stars, or from cosmic rays slamming into gas clouds. The debate rages on, with some researchers arguing the signal's smoothness points to dark matter, while others insist it's too lumpy, better explained by conventional astrophysics. What makes this hunt so thrilling and so frustrating is the sheer audacity of the challenge. Dark matter annihilation signals would be extraordinarily faint, drowned out by the universe's natural fireworks. Separating a potential dark matter signal from the cosmic background is like listening for a single violin in a symphony orchestra. To sharpen their search, scientists have turned to dwarf galaxies, small, dim satellites of the Milky Way that are thought to be brimming with dark matter and relatively free of gamma-ray pollution. If dark matter annihilates anywhere, these pristine environments should offer the clearest view. Yet even here, the results are ambiguous. Some dwarfs show faint gamma-ray hints, while others remain stubbornly silent, leaving theorists to wonder, are we looking for the wrong particle, or is annihilation rarer than we predicted? The stakes couldn't be higher. A confirmed detection wouldn't just prove dark matter's existence, it would reveal its nature. Different particles annihilate into different byproducts, gamma rays, neutrinos, even antimatter like positrons. Each signature acts like a barcode, encoding clues about dark matter's mass and how it interacts. The Pamela and Amos-02 experiments, for instance, have detected unexpected surges of positrons in cosmic rays, sparking speculation that dark matter might be decaying or annihilating nearby. But like the gamma-ray excess, alternative explanations like pulsars complicate the story. This is the razor's edge of modern astrophysics. Every potential signal could be a breakthrough or a dead end. The Fermi-LAT team continues to refine its data, teasing out subtler patterns. Next-generation telescopes, like the proposed E-astrogam, promise even sharper vision, capable of spotting fainter or faster-moving particles. With each observation, we're not just testing one theory but probing the boundaries of physics itself. Whether the galactic center excess fades into obscurity or emerges as dark matter's smoking gun, one thing's certain: the universe is daring us to look deeper, to listen more carefully, and to stay open to the possibility that the answers we seek might be hiding in the most unexpected places. Neutrinos are the universe's most elusive escape artists, particles so ghostly they pass through entire planets like they aren't even there. Born in the hearts of stars, supernova, and even nuclear reactors, these tiny wanderers barely interact with matter at all. A neutrino could slice through a block of lead light-years thick without slowing down. Given their stealthy nature, you might wonder, could these phantoms be part of dark matter's hidden identity? The answer is a tantalizing mix of yes and no, with a twist that takes us into the realm of hypothetical particles even stranger than the ones we've detected. Ordinary neutrinos, while mysterious, are far too hot to account for dark matter's gravitational grip. In cosmology, hot doesn't mean temperature, it describes how fast particles move. Neutrinos zip through space at nearly the speed of light, their high velocities making them terrible candidates for the slow, clumping behavior dark matter exhibits. Think of it like trying to build a sandcastle with grains that won't stay put. The cosmic web's delicate filaments and galaxy clusters require cold, dark matter, particles sluggish enough to coalesce under gravity's pull. Neutrinos, by contrast, would have smeared the universe's structure into a featureless haze long ago. Observations of galaxy formation rule them out as the primary culprit. But what if there's another flavor of neutrino we haven't met yet? Enter sterile neutrinos, a hypothetical heavyweight cousin to the ones we know. Unlike their ordinary counterparts, sterile neutrinos wouldn't dance to the tune of the weak nuclear force, making them even more aloof from ordinary matter. Their added mass could slow them down enough to behave like cold, dark matter, while their reluctance to interact would explain why we haven't spotted them. Picture a room where one neutrino chats occasionally with the furniture, while its sterile sibling phases straight through the walls without a whisper. The hunt for sterile neutrinos is a detective story playing out in particle accelerators and nuclear reactors. Experiments like Fermilab's Mini BUNI have reported anomalous results, tiny excesses of neutrino oscillations that could hint at a fourth sterile flavor. Other researchers scour the skies for X-ray signals that might betray sterile neutrinos decaying in distant galaxy clusters. A faint, unexplained emission line spotted in multiple datasets, dubbed the 3.5 kilo electronvolt line, has sparked speculation that sterile neutrinos might be annihilating in the depths of space, leaving behind a spectral calling card. If sterile neutrinos exist, they'd be a game changer not just for dark matter, but for particle physics as a whole. Their discovery would demand an expansion of the Standard Model, the playbook governing all known particles and forces. They could also solve lingering mysteries like why neutrinos have mass at all, a question that still puzzles physicists decades after their discovery. Most compellingly, sterile neutrinos might bridge the gap between the invisible and visible cosmos, offering a rare glimpse into how dark matter's shadowy realm connects to our own. Yet the case remains wide open. Every anomalous signal could also stem from mundane astrophysical processes or experimental noise. The 3.5 kilo electronvolt line might fade under closer scrutiny, just as other dark matter candidates have. What's undeniable is that sterile neutrinos represent a fascinating what-if, a reminder that the universe's secrets often lurk just beyond the edge of our current understanding. Whether they're real or not, their story underscores a deeper truth. Dark matter might not be one thing, but many, a tapestry of invisible particles, each weaving their own thread into the cosmos' grand design. Black holes aren't just cosmic vacuum cleaners lurking in galaxy centers. They might also be relics from the universe's first moments, hiding in plain sight as dark matter. Imagine the cosmos just a fraction of a second after the Big Bang, a seething cauldron of energy where density fluctuations could have collapsed directly into black holes. These wouldn't be the stellar mass black holes we know today, forged from dying stars, but primordial black holes, or PBH, born from the raw chaos of creation itself. Ranging in size from a speck of dust to a massive star, they drift through space like invisible anchors, their gravity subtly tugging at everything around them. If they exist, they could solve two mysteries at once: the nature of dark matter and the origins of the universe's earliest black holes. The beauty of PBHs lies in their simplicity. Unlike exotic particles dreamed up by theorists, black holes are a known quantity, just ones we can't see unless they're actively feeding. A PBH could sit right beside us, invisible, its only giveaway the faintest warp in space-time. But how do you hunt something that emits no light? Astronomers have two clever tricks up their sleeves. First, microlensing. When a PBH passes in front of a distant star, its gravity bends the star's light like a lens, causing a brief brightening. Projects like the Optical Gravitational Lensing Experiment, or OGLE, have scanned millions of stars for these telltale flashes, placing tight limits on how many PBHs could be lurking in our galactic neighborhood. The second method listens for the echoes of PBHs colliding. Gravitational wave observatories like LIGO and Virgo detect ripples in spacetime from black hole mergers, and while most events involve stellar remnants, a few could be primordial survivors crashing together after billions of years in the dark. The data so far paints a nuanced picture. PBHs can't be all the dark matter. There simply aren't enough microlensing events or mergers to account for the universe's missing mass. But they might play a supporting role, especially if they cluster in specific ways. Some theories suggest PBHs could explain oddities like the unexpectedly heavy black holes LIGO has spotted, or the way certain galaxies seem to lack dark matter in their cores. Others propose that PBHs seeded the supermassive black holes found in galactic centers, growing over eons by swallowing gas and stars, the most tantalizing idea. PBHs might not even be black holes as we know them, but something stranger, like remnants of collapsed extra dimensions or bubbles from a multiverse. What makes PBHs so compelling is their dual nature. They're both a conservative hypothesis, black holes are real, after all, and a radical one, suggesting the cosmos is littered with ancient artifacts we've overlooked. Every unexplained gravitational wave signal, every anomalous star flicker could be a clue, and if PBHs do lurk out there, they'd be more than dark matter candidates. They'd be time capsules from the universe's violent infancy, carrying secrets about how everything began. The The hunt continues not just with telescopes and detectors, but with simulations probing how PBHs would shape galaxy formation, or how their evaporating radiation might leave faint imprints in the cosmic microwave background. Whether they're a minor player or a major piece of the puzzle, primordial black holes remind us that sometimes the darkest corners of the universe hold the brightest sparks of discovery. Supersymmetry whispers a tantalizing possibility that for every particle we know, there's a hidden twin lurking just beyond our reach. This elegant theory, affectionately called SUSY, suggests electrons, quarks, and photons all have heavier superpartners waiting to be discovered. Imagine a cosmic mirror where familiar particles reflect into a shadow realm of sparticles, selectrons, squarks, photons, each with properties that could solve some of physics' deepest puzzles. Among these hypothetical superpartners, one stands out as a prime dark matter candidate, the Neutrino. This elusive particle, a mix of superpartners to photons and Z-bosons, would be stable, electrically neutral, and nearly invisible, perfect traits for the universe's missing mass. For decades, SUSY has been more than just a dark matter theory. It's been a grand unification dream. By balancing the equations of particle physics, it could explain why gravity is so weak compared to other forces, or why the Higgs boson is surprisingly light. SUSY mathematical beauty lies in its symmetry, a kind of cosmic harmony that would tie together all fundamental forces at incredibly high energies. It's as if the universe's rulebook has hidden pages, and SUSY offers the key to reading them. The theory's elegance has made it a favorite among physicists, even as experimental proof remains elusive. The Large Hadron Collider was supposed to be SUSY proving ground. Smashing protons at near-light speeds, scientists hope to create superpartners in the debris, their presence revealed by missing energy in the collisions. Yet run after run, the LHC found no trace of sparticles. Some researchers grew disillusioned, watching their once promising parameter spaces shrink with each null result. But others argue SUSY might simply be heavier than expected, or that superparticles decay in ways that evade current detectors. The hunt isn't over. Upgraded colliders or even cosmic ray observations could yet reveal SUSY fingerprints. What keeps theorists clinging to SUSY isn't just stubbornness, it's the sheer explanatory power it holds. If neutralinos exist, they'd naturally cluster in galactic halos, their weak interactions matching dark matter's observed behavior. They'd also solve the WIMP miracle, where particles with weak scale masses and interactions happen to leave just the right relic abundance from the Big Bang. It's as if the universe left breadcrumbs pointing straight to SUSY doorstep. Even without direct detections, indirect hints, like anomalous muon measurements or unexpected Higgs boson properties, keep the hope alive that supersymmetry might be real, just hiding in a corner we haven't probed deeply enough. The stakes couldn't be higher. Discovering SUSY would be like finding the Rosetta Stone of physics, translating between the quantum world and cosmic scales. It wouldn't just explain dark matter, it would reshape our understanding of reality's building blocks, offering clues about the universe's earliest moments and its ultimate fate. Until then, SUSY remains a breathtaking what-if, a reminder that sometimes the most profound truths are the ones just beyond our grasp, waiting for the right experiment, the right moment to step into the light. Einstein's cosmological constant paints dark energy as an unchanging force, a steady pressure woven into the fabric of space itself. But what if that's only half the story? A growing chorus of theorists suggests dark energy might not be constant at all. It could ebb and flow, growing stronger or weaker over cosmic time. Imagine a river that suddenly changes its current, first lazily meandering, then surging with unexpected force. If dark energy behaves this way, it wouldn't just tweak our models, it would rewrite the universe's destiny. This idea isn't pure speculation. Observations of distant supernova, the same celestial beacons that first revealed cosmic acceleration, hint at subtle shifts in expansion rates across different epochs. Some datasets suggest dark energy was slightly weaker in the universe's youth, as if it's been gathering strength over billions of years. Other clues come from baryon acoustic oscillations, frozen ripples in the distribution of galaxies that act as cosmic yardsticks. By measuring how these patterns stretch at different distances, astronomers can reconstruct the expansion history with exquisite precision, searching for any deviation from Einstein's static cosmological constant. Enter DEFY and Euclid, two groundbreaking surveys designed to probe these mysteries. The Dark Energy Spectroscopic Instrument, or DEFY, maps millions of galaxies and quasars across 11 billion years of cosmic time, creating a 3D atlas of the universe's large-scale structure. Meanwhile, the Euclid Space Telescope peers even deeper, its infrared eyes capturing light from galaxies so distant their light has traveled for most of the universe's history. Together, they're testing whether dark energy's push has remained uniform or if it pulses like a heartbeat, subtly altering the cosmos expansion rhythm. The implications are staggering. If dark energy strengthens over time, it could trigger a big rip, shredding galaxies, stars, and even space-time itself in a catastrophic finale. If it weakens, gravity might regain dominance, pulling the universe back into a fiery collapse. Even small fluctuations could reshape the cosmic web's growth, altering how galaxies cluster and evolve. It's a reminder that dark energy isn't just some abstract placeholder in equations. It's the architect of reality's ultimate fate, and we're only beginning to decode its blueprints. Yet the challenges are immense. Measuring dark energy's potential evolution requires comparing the universe's expansion across vast stretches of time, a task riddled with uncertainties. Dust clouds, galactic collisions, even the peculiar motions of galaxy clusters can muddy the signals. Some researchers argue current anomalies are mere statistical flukes, while others see them as cracks in the standard model's foundation. The debate won't be settled by a single experiment, but by a convergence of evidence: supernova, galaxy surveys, gravitational lensing, all pointing toward a common conclusion. What makes this quest so thrilling is its sheer audacity. We're not just studying the universe as it is, we're reconstructing its history like cosmic detectives, piecing together how dark energy's influence has waxed or waned across eons. The answers won't just fill textbooks, they'll reveal whether the cosmos is headed toward eternal expansion, dramatic collapse, or something even stranger. Every new data point brings us closer to knowing whether Einstein's greatest blunder was truly a constant, or if the universe has been hiding a dynamic secret all along. At the heart of modern cosmology lies a puzzle so stubborn it threatens to unravel our understanding of the cosmos. When astronomers measure how fast the universe is expanding, a number called the Hubble constant, they get different answers depending on which cosmic ruler they use. Study distant supernova and you'll land on one value. Analyze the afterglow of the Big Bang and you'll get another. These results aren't just slightly off, they're disagreeing by enough to suggest something fundamental is missing from our equations. This mismatch, known as the Hubble tension, isn't just a technical hiccup. It's a flashing neon sign pointing to gaps in our knowledge, possibly even clues to new physics lurking beyond the edges of current theory. Take the cosmic microwave background, or CMB, that ancient light from the universe's infancy. By studying its subtle temperature fluctuations, scientists can calculate how fast space was stretching shortly after the Big Bang, then extrapolate to today's expansion rate. This method, honed by satellites like Planck, gives a Hubble constant of about 67 kilometers per second per megaparsec. Now switch to observing pulsating stars called Cepheids in nearby galaxies, or Type 1a supernova, the universe's standard candles, and the number jumps to roughly 73. That 7% gap might sound small, but over cosmic distances, it adds up to a glaring inconsistency. It's like two clocks, both precisely calibrated, ticking at different speeds with no explanation why. The most thrilling possibility, the tension might be revealing cracks in our standard model of cosmology. Maybe dark energy isn't constant but evolves over time, subtly altering the expansion rate in ways we haven't accounted for. Some theories propose it could interact with dark matter, transferring energy in hidden ways that skew our measurements. Others suggest exotic early universe phenomena, like a brief phase of early dark energy that tweaked the cosmos expansion before fading away. Then there's the radical notion that dark matter itself might have properties beyond our current understanding. Perhaps a fraction of it decays over eons, injecting extra energy into the cosmic fabric. But before we rewrite physics textbooks, there's the mundane yet crucial question: could the discrepancy stem from measurement errors? Astronomers have scrutinized their tools for flaws. Maybe Cepheid stars aren't as uniform as we thought, or supernova dim in unexpected ways. Teams have cross-checked with entirely independent methods, like gravitational lensing of quasars or the vibrations of baryonic matter in galaxy clusters. Yet the tension persists, stubborn as ever, tightening the case that this isn't just noise, it's a signal. What makes the Hubble tension so electrifying is its sheer universality. Resolving it could demand more than tweaking a few parameters. It might require reimagining pillars of modern cosmology, from the nature of dark energy to the very geometry of spacetime. Future telescopes like the Nancy Grace Roman Space Telescope or the Vera Rubin Observatory aim to settle the debate with unprecedented precision. Until then, the tension remains a tantalizing riddle, one that reminds us how much we still have to learn about the cosmos' grand design. Whether the answer lies in overlooked details or revolutionary new physics, one thing's certain: the universe is still full of surprises. Dark matter isn't just a passive backdrop to the universe. It's the invisible architect behind every galaxy we see. Picture the early cosmos as a vast, turbulent sea of gas, too hot and chaotic for stars to form on their own. Without dark matter's gravitational embrace, that gas would have remained diffuse, like smoke drifting endlessly in the wind. But dark matter's pull changed everything. Its halo's massive, invisible cocoons created gravitational wells deep enough to trap hydrogen and helium, compressing them until they ignited into the first stars. These primordial halos became the universe's first construction sites, gathering raw materials and assembling them into the galaxies we recognize today. Computer simulations reveal just how critical dark matter was to this process. Run a model without it, and the gas never clumps efficiently. The universe remains a formless haze. Add dark matter, and within billions of simulated years, intricate webs of galaxies emerge, mirroring the real cosmos with uncanny accuracy. The reason: dark matter's gravity is relentless, unaffected by the pressure of radiation or the pushback of magnetic fields that buffet ordinary matter. While atoms scatter and rebound, dark matter steadily accumulates, drawing gas into its grasp like an invisible hand shaping clay. This is why galaxies aren't randomly scattered. They trace the underlying scaffolding of dark matter, clinging to its filaments like pearls on a string. The fingerprints of this process are everywhere. Dwarf galaxies, for instance, are dominated almost entirely by dark matter, with so few stars that they're practically translucent against the night sky. Their existence makes no sense without dark matter's gravitational anchor. There's simply not enough visible mass to hold them together. Even in grand spirals like the Milky Way, stars on the outskirts orbit at speeds that defy the laws of gravity, unless you account for the colossal dark matter halo enveloping them. These halos aren't static either. They grow over time, merging with others in slow-motion collisions that send ripples through the cosmic web. When two galaxies unite, their dark matter halos intertwine first, dictating how the visible matter will follow. But dark matter's role isn't just about brute force, it's about precision. The way galaxies spin, the way they cluster, even the way they're distributed across the sky all hinge on dark matter's subtle influence. Take the Tully-Fisher relation, a curious link between a galaxy's brightness and its rotation speed. Without dark matter, this relationship would be a messy scatter plot. Instead, it's a clean, predictable line, a testament to how dark matter's gravity harmonizes the chaos of star formation. Even the universe's emptiest regions, the voids where galaxies are scarce, owe their existence to dark matter. These barren stretches are where dark matter's pull was too weak to gather gas, leaving behind cosmic deserts amid the stellar cities. What's astonishing is how much we've pieced together without ever seeing dark matter directly. Like detectives reconstructing a crime scene from footprints, astronomers trace its presence through the motions of stars, the bending of light, and the echoes of the Big Bang. Every new observation adds another brushstroke to the portrait of an invisible force that shaped everything from the tiniest dwarf galaxy to the grandest supercluster. And as simulations grow more sophisticated, they're revealing something even more profound. Without dark matter, the night sky wouldn't just be different. It would be nearly empty. No spirals, no ellipticals, no glittering bands of starlight, just a lonely sea of unlit gas, adrift in the dark. We're standing on the brink of a new era in dark matter research, where cutting-edge experiments and revolutionary telescopes are poised to peel back the veil on the universe's greatest mystery. Imagine detectors so sensitive they could hear the faintest whisper of a dark matter particle brushing past an atom, or telescopes powerful enough to trace the invisible scaffolding of the cosmos with pinpoint precision. That's the promise of next-generation projects like LUX Zeppelin, or LZ, a vat of ultra-pure liquid xenon buried a mile underground, shielded from cosmic noise, waiting for the once-in-a-lifetime collision that could change physics forever. LZ's predecessors, like Xeno NNT, have already pushed sensitivity to unprecedented levels, ruling out swaths of potential dark matter candidates. But LZ takes it further, with a design so refined it could spot particles interacting with ordinary matter as rarely as once every century. Then there's Darwin, the ambitious successor to LZ, planned to be the largest and most sensitive dark matter detector ever built. Picture a chamber holding tens of tons of liquid xenon, its atoms acting like a vast net cast into the cosmic dark. Darwin's scale isn't just about brute force, it's about statistics. The more atoms in the target, the higher the chance of catching a dark matter particle, even if they're as elusive as whispers in a hurricane. But Darwin's ambitions stretch beyond dark matter. It could also detect neutrinos from the sun's core or even probe the mysterious nature of quantum mechanics itself, proving that the quest for dark matter often unlocks doors to other enigmas along the way. While underground labs hunt for direct collisions, cosmologists are turning to the skies with projects like CMB-S4, a next-generation array of telescopes designed to study the cosmic microwave background with razor-sharp clarity. The CMB is already our most powerful snapshot of the early universe, but CMB-S4 will amplify its secrets 100-fold. By mapping subtle distortions in this ancient light, scientists can infer dark matter's distribution with unmatched detail, testing whether it clumps exactly as predicted or if there are surprises, hints of self-interactions, hidden substructures, or even entirely new physics. It's like upgrading from a blurry black and white photo to a high-resolution 3D scan of the cosmos' infancy. Space telescopes are joining the hunt too, with instruments like JWST and the upcoming Nancy Grace Roman telescope set to revolutionize our view of dark matter's cosmic choreography. JWST infrared eyes peer through dust and time, capturing the faintest galaxies born in the universe's youth, their shapes warped by dark matter's gravity. The Roman telescope, meanwhile, will conduct a sweeping survey of the sky, measuring how dark matter bends light from millions of galaxies, a technique called weak gravitational lensing. Together, these observatories will create the most detailed maps yet of dark matter's hidden web, revealing how it guides the formation and evolution of galaxies across eons. Coming decades won't just bring incremental progress, they could deliver paradigm shifts. If detectors like LZ or Darwin strike gold, we might finally hold dark matter's identity in our hands, confirming whether it's WIMP, axions, or something entirely unforeseen. But even if these experiments come up empty, their null results will force us to rethink fundamental assumptions, perhaps pivoting to wilder ideas like primordial black holes or extra-dimensional particles. Science thrives on both discovery and dead ends, and dark matter's elusiveness guarantees one thing: the journey ahead will be anything but predictable. Whether through direct detection or revolutionary theory, the next chapter in this cosmic detective story promises to rewrite our understanding of the universe's hidden foundations. The fate of the universe isn't written in the stars. It's etched into the enigmatic behavior of dark energy, a force so mysterious it could steer the cosmos toward dramatically different endings. Picture a universe where dark energy's repulsive push remains steady, as Einstein's cosmological constant suggests. Over trillions of years, galaxies would recede until their light fades from view, stars burn out, and space stretches into an endless frozen void. This Big Freeze scenario isn't just poetic melancholy, it's the most straightforward prediction of our current models. Without dark energy's grip loosening, the universe would face a slow but inevitable heat death, where even black holes evaporate into faint whispers of radiation, leaving behind a lifeless expanse colder and darker than we can fathom. But dark energy might not play by such predictable rules. Some theories suggest it could grow stronger over time, its repulsive force accelerating until it overpowers gravity, electromagnetism, even the nuclear bonds holding atoms together. In this Big Rip scenario, galaxies would be torn apart first, then solar systems, planets, and eventually the very fabric of spacetime. The universe would end not with a whimper, but with a catastrophic rending of reality itself. This isn't science fiction. Calculations show that if dark energy's density increases, it could shred all structures in a finite time, perhaps tens of billions of years from now. The irony, the same force driving cosmic expansion today could one day annihilate everything it helped create. There's a third, equally dramatic possibility: dark energy might decay. If its strength diminishes, gravity could regain dominance, reversing the expansion and pulling the universe back into a fiery collapse. Imagine galaxies rushing toward one another, their light blue-shifting as space contracts, until everything crashes together in a big crunch, a cosmic mirror of the Big Bang. Some models even propose this collapse could trigger a new universe, birthing an endless cycle of expansion and contraction. While evidence currently favors eternal expansion, the idea of a cyclic cosmos lingers, offering a poetic symmetry to existence. What makes these scenarios more than just speculative tales is their grounding in observable reality. The key lies in something called the equation of state, a simple ratio describing dark energy's pressure and density. If this value equals exactly -1, dark energy is constant, dooming us to the big freeze. If it dips below, the big rip becomes inevitable. If it rises towards zero, the big crunch looms. Current measurements hover near -1, but with margins of error that leave room for surprises. Projects like the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope are racing to refine these measurements, hunting for even tiny deviations that could tilt the universe's fate toward one of these extremes. The stakes couldn't be higher. Dark energy isn't just another puzzle, it's the arbiter of reality's ultimate destiny. Whether the cosmos ends in ice, fire, or rupture depends entirely on properties we've yet to pin down. And while these scenarios unfold on timescales incomprehensible to human life, understanding them reshapes our place in the universe's story. We're not just observers of cosmic history, we're its interpreters, piecing together clues that will outlast our species, our planet, even our galaxy. The study of dark energy isn't just about mapping the universe's end. It's about uncovering the hidden rules that govern existence itself. The cosmological constant might be the simplest explanation for dark energy, but what if the truth is far stranger? Enter quintessence, a theory that paints dark energy not as a static force, but as a dynamic field swirling through space, its strength ebbing and flowing over cosmic time. Named after the ancient Greek fifth element, quintessence imagines dark energy as something alive, evolving alongside the universe itself. Picture a cosmic tide, sometimes surging to accelerate expansion, other times receding to let gravity take the lead. This isn't just poetic speculation, it's a serious attempt to explain dark energy's most puzzling feature, its eerily fine-tuned value. If quintessence is real, it could mean the universe's expansion isn't destined for a steady chill, but for a future shaped by the unpredictable rhythms of an invisible, energy-shaping tide. But quintessence isn't the only daring idea on the table. Some theorists look beyond our familiar four dimensions, suggesting dark energy could be a shadow cast by hidden realms. In models inspired by string theory, gravity might leak into extra dimensions, weakening its apparent strength in our visible universe. This leakage could mimic the effects of dark energy, creating the illusion of cosmic acceleration without invoking any new fields or particles. Imagine blowing up a balloon with tiny holes. The air escaping unseen could make the balloon expand faster than expected, just as hidden dimensions might make space stretch in ways we don't fully grasp. It's a radical reimagining of reality, where the answers to dark energy's riddles lie not in what we observe, but in dimensions we can't yet perceive. Then there's the holographic principle, a mind-bending concept borrowed from black hole physics. It proposes that our three-dimensional universe might actually be a projection of information encoded on a distant, two-dimensional surface, like a cosmic version of a hologram sticker. In this framework, dark energy could emerge naturally from the way information is stored and processed at the universe's boundaries. Think of it like a computer simulation running out of memory. As the universe grows, the way it encodes data might introduce a kind of pressure that drives accelerated expansion. While this sounds like science fiction, it's grounded in serious math, offering a way to unify quantum mechanics and gravity while explaining dark energy's peculiar behavior. What ties these theories together is their willingness to challenge bedrock assumptions. The cosmological constant fits the data well, but it feels like a placeholder, a mathematical stopgap rather than a deep explanation. Alternative ideas, however speculative, push us to ask harder questions. Could dark energy's value seem fine-tuned because it's not fundamental but emergent? Might it be intertwined with the very fabric of space-time in ways we've yet to articulate? The most exciting aspect isn't just their potential to solve the dark energy puzzle, but their ability to reshape our understanding of reality itself. For now, these theories remain in the realm of possibility, their predictions just beyond the reach of current experiments. But next-generation telescopes like Euclid and DEFY are designed to hunt for subtle clues, tiny variations in cosmic expansion that could betray quintessence's presence, or anomalies in the large-scale structure of the universe that hint at extra dimensions. Whether any of these ideas survive future tests, they serve as a testament to science's greatest strength, the courage to imagine radically different worlds in pursuit of truth. After all, the universe has never been bound by human expectations. Why should our theories be? The standard model of particle physics is a triumph of human ingenuity, a meticulously crafted framework that explains nearly everything we observe in the quantum realm, from the electrons powering our devices to the gluons binding atomic nuclei. Yet for all its precision, it has a glaring blind spot: dark matter. This invisible cosmic architect, responsible for sculpting galaxies and guiding the universe's structure, doesn't fit into the model's elegant equations. It's as if we've assembled a 1,000-piece puzzle only to realize the box contained an extra piece with no place to slot it in. The standard model simply wasn't built to account for a particle that barely interacts with light or matter, yet wields gravitational influence on a galactic scale. This isn't just a minor oversight, it's a beacon pointing toward undiscovered physics. The model's inability to explain dark matter mirrors past moments of scientific upheaval, like when the discovery of radioactivity forced physicists to expand their understanding of atomic structure. The Higgs boson, detected in 2012, was once such a missing piece, confirming a mechanism that gives particles mass. Finding dark matter's counterpart could trigger a similar revolution, bridging the chasm between the infinitesimally small and the astronomically large. Imagine a theoretical thread tying the behavior of subatomic particles to the motion of galaxy clusters, a unified framework where quantum weirdness and cosmic gravity finally shake hands. The hunt for this missing piece has spawned countless hypotheses, each proposing its own candidate to extend the standard model. Weakly interacting massive particles, or WIMP, emerged as early favorites because they naturally slot into supersymmetry, a theory predicting every known particle has a heavier twin. Axions born from quantum puzzle solving offer another path, their ghostly lightness contrasting with WIMP's heft. Then there are sterile neutrinos, hidden sector particles, and even primordial black holes, each possibility stretching the model's boundaries in new directions. What unites them is their potential to transform cosmology and particle physics from separate disciplines into chapters of the same story. The stakes extend far beyond academic curiosity. If dark matter particles interact through forces outside the standard model, they could open portals to an entirely hidden sector of reality. Picture a shadow universe where dark matter isn't solitary but part of a rich ecosystem, with its own particles, forces, and perhaps even complexity we can't yet fathom. Some theories suggest dark matter might occasionally decay or annihilate, emitting faint signals we could detect. Others propose it interacts weakly with ordinary matter through a dark photon, a carrier of a fifth fundamental force. Every experiment hunting for these phenomena, whether in underground labs, particle colliders, or space telescopes, isn't just searching for a missing ingredient. They're probing the edges of known physics, testing whether our universe's rulebook needs a sequel. What makes this search so electrifying is its unpredictability. The standard model has survived every test thrown at it for decades, but dark matter's defiance hints at cracks in its foundation. discovering its true nature could do more than fill a gap. It might reveal that the model is just one layer of a far deeper reality. Like uncovering that the ocean's surface, which once seemed like the entirety of the sea, actually hides entire worlds beneath. Whether the breakthrough comes from a lab, a telescope, or a theoretical leap, one thing is certain: the story of dark matter isn't just about what's missing. It's about what's waiting to be discovered. Cosmic inflation and dark energy might seem like entirely separate chapters in the universe's story, one describing its explosive birth, the other its accelerating present, but hidden beneath the surface. They could be two sides of the same cosmic coin. Picture the universe in its first fraction of a second, expanding faster than the speed of light, doubling in size countless times over in a blink. This was inflation, driven by a mysterious field that flooded space with repulsive gravity, stretching the cosmos from smaller than an atom to the size of a grapefruit almost instantly. Then, just as abruptly, inflation switched off, its energy transforming into the matter and radiation that would later form stars and galaxies. Now, fast forward 14 billion years, and we see dark energy doing something eerily similar, pushing galaxies apart with a repulsive force that echoes inflation's signature move. The parallels are too striking to ignore. Both phenomena involve a form of energy that counteracts gravity's pull, causing space itself to stretch at an accelerating rate. But here's the puzzle: inflation was a fleeting burst, while dark energy appears to be a slow, steady pressure. Why did one fade while the other lingers? Some theorists propose their manifestations of the same underlying mechanism, a cosmic seesaw where inflation's energy didn't entirely vanish but instead diluted into the faint, persistent hum we now call dark energy. Imagine a volcano erupting violently, then settling into a quiet but endless seep of lava. The same forces are at work, just operating on vastly different scales. This idea could solve one of dark energy's deepest mysteries: its absurdly tiny but non-zero density. If dark energy is the diluted remnant of inflation, its weakness makes perfect sense. Over billions of years, the universe's expansion would have stretched inflation's energy thin, leaving behind just a whisper of its original strength, enough to nudge galaxies apart, but not so much that it tore the cosmos apart in its infancy. It's like finding a single drop of perfume in an empty warehouse. The scent is faint, but it hints at a once powerful presence. Unifying inflation and dark energy isn't just a neat theoretical trick, it could rewrite our understanding of cosmic evolution. If they're linked, then dark energy isn't an accident. It's a natural consequence of how the universe began. This would mean the fate of the cosmos was sealed in its first moments, with inflation's energy subtly shaping everything from the largest galaxy clusters to the void between them. Future experiments, like precision measurements of the cosmic microwave background or gravitational wave detectors sensitive to primordial ripples, might uncover clues to this connection. The answers could reveal not just where the universe is headed, but how its earliest moments set the stage for everything that followed. Yet the challenges are immense. Inflation's energy scale is trillions of times stronger than dark energies, making it hard to see how one smoothly transitions into the other. Some models propose extra dimensions or exotic fields to bridge the gap, while others suggest dark energy might not be constant at all, but a fading echo of inflation's final pulses. The truth might lie somewhere beyond our current math, waiting for a visionary insight to tie it all together. What's certain is that the link between these two cosmic forces, one that launched the universe, the other that will define its end, holds the key to understanding reality's grandest arc. And that's a story worth telling. Dark matter and cosmic energy don't just reshape our models of the universe, they shatter our assumptions about reality itself. Think about this. Everything you've ever seen, touched, or measured, every star, every planet, every speck of dust adds up to less than 5% of existence. The rest is a shadow realm, invisible and untouchable, yet dictating the fate of the cosmos. It's as if we've been staring at a painting, only to realize we've missed 95% of the canvas. This isn't just a gap in knowledge, it's a fundamental redefinition of what real even means. This revelation forces a profound humility. For centuries, science has operated on the belief that observation and measurement could eventually unveil all of nature's secrets. But dark matter and cosmic energy mock that confidence. They remind us that the universe isn't obligated to make sense to us, that our tools and senses might be woefully inadequate for grasping the full picture. Even our most advanced detectors, buried miles underground or orbiting in space, have so far come up empty. It's a cosmic irony. The more we learn, the more we realize how much lies beyond our reach. Yet there's a thrilling counterpoint to this humility. These mysteries don't just humble us, they ignite our imagination. The fact that we've deduced the existence of forces we can't see through sheer ingenuity and persistence is a testament to human curiosity. Consider Vera Rubin staring at galaxy rotation curves and daring to propose an invisible scaffolding holding them together, or the teams studying supernova realizing the universe wasn't just expanding but accelerating, as if pushed by some unseen hand. These breakthroughs didn't come from accepting the limits of our senses but from questioning them, from trusting math and inference when our eyes failed us. What's even more awe-inspiring is how these discoveries redefine emptiness. We used to think of space as a void, a blank stage where matter performs. Now we know it's anything but empty. Dark matter weaves through it like an invisible net, and dark energy hums in the spaces between galaxies, stretching the fabric of reality itself. The universe isn't just full of secrets, it is the secret, a riddle wrapped in equations and whispered through gravitational echoes. This shift in perspective has philosophical ripples far beyond astronomy. It challenges the very way we frame questions about existence. If most of reality is hidden, what else might we be missing? Could there be layers of physics even stranger than dark matter, waiting to append our theories again? The history of science is littered with moments where the obvious turned out to be a mirage. The Earth wasn't the center of the universe. Time wasn't absolute. Particles could be in two places at once. Dark matter and cosmic energy are the latest in this lineage, proving that the cosmos will always outrun our assumptions. But perhaps the most beautiful lesson is this: the universe isn't just stranger than we imagine, it's stranger than we can imagine. Every time we peel back one layer, another, even more mysterious, waits beneath. And that's not a failure, it's an invitation to keep exploring, to stay curious, and to embrace the wonder of not knowing. After all, a universe without mysteries wouldn't just be boring, it wouldn't be real. One of the biggest hurdles in understanding dark matter and dark energy isn't the science itself, it's the myths and mix-ups that cling to these concepts like cosmic static. Take antimatter, for example. While it sounds like something straight out of science fiction, particles that annihilate normal matter in bursts of energy, it's actually a well-documented part of physics, used in PT scans and studied in particle colliders. Dark matter, on the other hand, doesn't explode or vanish on contact. It's more like a ghostly neighbor you never see but know is there because the lawn keeps getting mowed. Unlike antimatter, which we can create and observe, dark matter's presence is inferred solely through its gravitational handshake with the visible universe. Then there's the confusion with black holes. Both are invisible, both warp space-time, but that's where the similarities end. Black holes are cosmic vacuum cleaners, swallowing anything that strays too close, while dark matter is more like the scaffolding holding up the universe. It doesn't devour stars or bend light into fiery rings. It simply is a silent partner in the cosmic dance. The irony, dark matter is far more common than black holes. If you could magically see it, the night sky wouldn't be dotted with the occasional dark vortex. It would be filled with a shimmering web, threading through every galaxy and stretching across the voids between them. Dark energy suffers from its own misconceptions. It's often described as a force, evoking images of cosmic winds pushing galaxies apart, but that's not quite right. Imagine space itself as a stretchy fabric. Dark energy isn't a hand tugging at the edges, it's the fabric's inherent tendency to expand, woven into the very structure of reality. Unlike gravity or electromagnetism, it doesn't pull or push matter, it alters the stage beneath the actor's feet. This subtle distinction matters because it changes how we think about the universe's fate. A force might fade or reverse, but a property of space, that's harder to undo. The root of these mix-ups often lies in language. Terms like dark and energy carry baggage, conjuring images of shadowy villains or sci-fi power sources. In reality, dark just means unseen, and energy is a placeholder for something we don't yet fully understand. The gap between scientific terminology and public perception isn't just a trivia challenge. It shapes how people engage with groundbreaking discoveries. When dark matter is conflated with something destructive or rare, it becomes harder to grasp its true role as the universe's invisible architect. Demystifying these ideas starts with reframing the conversation. Dark matter isn't a cosmic anomaly, it's the norm, the hidden bulk of reality. Dark energy isn't a mysterious force, but a feature of the universe as fundamental as time or space. The more we untangle these concepts from pop culture's grip, the closer we get to a shared understanding of the cosmos, one where the unseen isn't feared but explored, where the mysteries we can't touch are just as real as the ones we can. Solving the mysteries of dark matter and cosmic energy isn't just a job for astronomers, it demands a symphony of expertise, blending astrophysics, particle physics, cosmology, and even cutting-edge technology. Imagine trying to decode an ancient manuscript written in multiple languages. You wouldn't rely on just one translator. You'd need historians, linguists, and cryptographers working in concert. That's exactly how modern science tackles these cosmic puzzles. Astrophysicists map the large-scale structure of the universe, tracing dark matter's gravitational fingerprints across galaxy clusters. Particle physicists design underground experiments to hunt for elusive dark matter particles, while cosmologists scrutinize the cosmic microwave background for clues about dark energy's influence over billions of years. Each field brings a unique lens, and together they paint a fuller picture of the invisible forces shaping our cosmos. One of the most transformative tools in this collaborative effort is machine learning, which sifts through mountains of data with superhuman efficiency. Telescopes like the Vera Rubin Observatory will soon flood researchers with hundreds of terabytes of images, more than any human team could analyze in a lifetime. Machine learning algorithms act as cosmic detectives, spotting subtle patterns in galaxy shapes that reveal dark matter's distribution or flagging anomalies in supernova brightness that might hint at dark energy's variability. These systems don't replace scientists, they amplify their reach, turning noise into actionable insights. It's like having 1,000 assistants combing through the universe's archives, each trained to recognize the faintest whispers of the unknown. Meanwhile, quantum sensors are pushing the boundaries of detection sensitivity, probing realms previously thought unreachable. Traditional experiments rely on massive detectors filled with liquid xenon or germanium, waiting years for a single dark matter particle to interact. Quantum technologies like superconducting qubits or atom interferometers operate at scales so precise they can sense disturbances tinier than an atom's width. Picture trying to hear a pin drop in a thunderstorm. Quantum sensors are like microphones fine-tuned to isolate that faint click. These advancements aren't just incremental, they're revolutionary, opening doors to discovering particles or forces that defy conventional detection. What makes this interdisciplinary approach so powerful is its ability to cross-pollinate ideas. A breakthrough in particle physics might inspire a new way to model galaxy formation. An oddity in cosmological data could send theorists back to the drawing board to rethink quantum fields. Even engineering plays a role, developing cryogenic systems to cool detectors near absolute zero or designing space telescopes with unprecedented precision. The lines between disciplines blur, revealing connections that might otherwise stay hidden. Collaboration isn't just helpful, it's essential. After all, the universe doesn't care about the boundaries we draw between fields of study. This convergence of expertise also highlights a deeper truth. The biggest questions in science can't be answered in isolation. Dark matter and dark energy aren't just astrophysical curiosities, they're bridges between the quantum and the cosmic, the infinitesimal and the infinite. Solving them requires more than brilliant minds. It demands a shared language, a willingness to venture beyond comfort zones, and an openness to ideas that might initially seem unrelated. Whether it's a particle physicist teaming up with a cosmologist or a computer scientist training an AI to spot cosmic anomalies, the path to discovery is paved with collaboration. And in that collective effort, we might just find the keys to the universe's best-kept secrets. Exploring the cosmos pushes the boundaries of human knowledge, but it also raises profound ethical questions. When governments allocate billions to build telescopes like the James Webb Space Telescope or particle colliders like the Large Hadron Collider, these investments spark debate. Should we prioritize studying distant galaxies when climate change, poverty, and disease demand urgent attention back on Earth? It's a delicate balancing act. Scientific discovery has undeniably transformed our daily lives. GPS, medical imaging, and even the internet itself trace their origins to fundamental research. Yet, the sheer scale of modern astrophysics projects forces us to ask whether the pursuit of cosmic understanding justifies diverting resources from immediate humanitarian needs. One perspective argues that curiosity-driven research is an intrinsic human endeavor, expanding not just our knowledge but our collective imagination. Breakthroughs often come from unexpected places. The same quantum mechanics that explained stellar fusion also gave us semiconductors, revolutionizing technology. Dark matter research might one day unlock new energy sources or propulsion systems we can't yet fathom. However, critics counter that such potential benefits are speculative, while hunger and inequality are real and present. The construction of the 30-meter telescope on Mauna Kea, for instance, faced fierce opposition from indigenous communities who view the mountain as sacred land. These tensions highlight how scientific ambition must navigate cultural, environmental, and social sensitivities, not just budgetary concerns. A compelling middle ground emerges when cosmic research directly addresses earthly challenges. Satellite technology developed for astronomy now monitors deforestation and natural disasters. Algorithms designed to map galaxy clusters help analyze climate data. Some projects, like the Square Kilometre Array Radio Telescope, intentionally include infrastructure that benefits local communities, from renewable energy grids to high-speed internet. This approach reframes the debate. Cosmic exploration isn't just about distant stars, but about refining tools that serve humanity in tangible ways. The key lies in intentional design, ensuring mega projects generate shared value beyond their primary scientific goals. Transparency and public engagement are equally critical. When taxpayers fund billion-dollar observatories, they deserve clarity on how these investments align with broader societal priorities. Citizen science initiatives like NASA's Zooniverse platform democratize discovery by letting the public classify galaxies or track asteroids from their laptops. These programs don't just educate, they foster a sense of collective ownership over cosmic research. Similarly, ethical frameworks for space exploration, like the Outer Space Treaty, remind us that scientific progress must be guided by principles of sustainability and equity, preventing the exploitation of celestial bodies or the creation of orbital debris that jeopardizes future missions. Ultimately, the ethical calculus hinges on legacy. The pyramids, the Parthenon, the great cathedrals. Humanity has always invested in endeavors that outlive individual generations. Cosmic research is no different. The data we gather today might seed solutions for crises we can't yet predict, just as Einstein's equations paved the way for technologies he never imagined. But this long-view thinking must coexist with short-term accountability, ensuring that the quest to understand the universe doesn't come at the cost of neglecting the world beneath our feet. The challenge isn't choosing between exploration and survival, it's weaving them together so that each elevates the other. Dark matter and cosmic energy aren't just scientific puzzles, they're the ultimate test of human curiosity, the kind of mysteries that force us to rethink everything we thought we knew. Imagine standing at the edge of a vast, uncharted ocean, knowing that beneath the surface lies an entirely hidden world shaping the waves above. That's where we are with these cosmic enigmas. Every flicker of data from deep space telescopes, every whisper of a signal in underground labs, could be the clue that cracks the case wide open. And what's at stake isn't just filling in a gap in our textbooks, it's rewriting the story of existence itself. Think about how far we've come already. A century ago, astronomers believed the Milky Way was the entire universe. Today, we're mapping the cosmic web, tracing dark matter's invisible threads, and measuring the repulsive force of dark energy across billions of light years. Yet for all that progress, the deeper we dig, the stranger the cosmos becomes. The fact that 95% of reality remains hidden from view isn't a failure, it's an invitation. An invitation to build better detectors, dream up bolder theories, and challenge the boundaries of known physics. This isn't just a job for scientists in lab coats. Breakthroughs could come from anywhere: a grad student's late-night calculation, an engineer's tweak to a telescope lens, or even an amateur astronomer spotting an anomaly in their backyard observations. History shows us that the biggest leaps often start with the simplest questions. Why do galaxies spin so fast? Why is the universe expanding faster, not slower? Every time we chase those questions, we're not just solving a puzzle, we're learning how to ask better ones. And let's be honest, the answers might be weirder than we can imagine. Maybe dark matter isn't one thing but many, a whole shadow universe of particles waiting to be discovered. Maybe cosmic energy is a sign of extra dimensions curling in on themselves, or evidence we're living in a multiverse. Or perhaps the truth is something no one's even dreamed up yet. That's the thrill of science at the frontier, the possibility that the next big idea is lurking just beyond the edge of our understanding, ready to turn everything we know on its head. So here's the real takeaway: the journey to unravel these mysteries isn't a straight line. It's a winding path full of dead ends, surprises, and moments of sheer wonder. Whether you're watching from the sidelines or diving into the research yourself, remember the universe doesn't owe us easy answers. but that's what makes the hunt so exhilarating. Because every time we think we've hit a wall, we find a crack, and behind that crack, well, that's where the next chapter begins.